Hey, Chunk. Yeah, I know I should be studying. Well, actually, passing your quals and working on your PhD is a lot like upgrading your Mario gameplay to Dr. Mario. In that, he's a little bit worse, and it'd be better off if you just hadn't bothered. Although if you do well, you do get bragging rights, and there's a reputation for being a bit of a jerk.
Woohoo! It's me! I didn't spend 7 years in residency for you to call me Mr. Mario.
Why am I doing this again? Let's talk about quotients. This is a really fun way to build a topological space. It's also, at least in my mind, the way to think about and conceptualize quotients when they show up in all sorts of other branches of mathematics. Here's the basic idea to have in mind. Quotients are just gluing. In a topological space, remember that we're always thinking in terms of nearness. So the idea is, maybe you got some stuff over here, maybe you got some stuff over there, and you just want them to be near to each other. Well, glue, and bam, you've got yourself a quotient. The end. Okay, so it's not that simple, although it really is that simple. In fact, this damn book goes about it all wrong by first defining what a quotient map is. And I mean, that's okay, but it's not going to give you the intuition, so we'll do quotient maps later. Here is the intuition. Start with some topological space X. Suppose you've got an equivalence relation on X. Okay, quick aside here, but an equivalence relation is just a relation that needs to be reflexive, symmetric, and transitive. That just means that A needs to be related to itself. If A is related to B, then B is related to A, and that if A is related to B and B is related to C, then A is related to C. Some examples are equality itself, congruence mod n, lying in the same preimage. A non-example is less than or equal to. Suppose you've got an equivalence relation on X. Then you can take the set of equivalence classes, X mod that relation. Okay, quick aside here, but an equivalence class is just a subset of elements that are all related to one another. We write brackets X, or sometimes X bar, for the set of elements related to X, and the set of equivalence class is just the set of all these X bars, or bracket X's. You can take the set of equivalence classes, X mod that relation, and give it a topology, where the open sets are those where the set of all the representatives is open in X. Explicitly, U is open in the quotient if the set of X's whose representatives are in U is open in X. In other words, U is open in the quotient if its preimage under the map P, which sends X to its equivalence class, is open in X. Since we're learning to be a little bit more sophisticated, we can say that this is the final topology that you put on the quotient with respect to the map P. Remember from last time that this means that it's the finest topology that makes the map P continuous. If you haven't seen equivalence relations before, then it might not be clear how this is supposed to represent gluing. But the basic idea is really intuitive. An equivalence relation is something that behaves like equality, and in the quotient set, X mod that relation, it is equality. The quotient topology is really just the topology you want to put where when you make equivalent things actually equal, their neighborhoods play nice now that they're the same point. Let's see it all play out with an example. Suppose we've got the unit disk. Let's define an equivalence relation where every point on the inside is just equivalent to itself, but every point on the boundary is equivalent to every other point on the boundary. Feel free to check for yourself that this is an equivalence relation. What is the resulting quotient space? Well, if we make every point on the boundary equal, then we've glued up the entire boundary into a single point. And we have to do this in a way that doesn't disturb nearness. So, watch. Thus, the quotient space is the sphere, S2. Ta-da! And the topology here is the totally natural one where nearness makes sense in this picture. There's no pathologies. Let's do a couple more examples for funsies. Here's a whole host of examples, which are all a lot like gluing the boundary of the disk to get the sphere. We're going to glue the boundaries of polygons in interesting ways. Throughout, it might be a good idea to check that the gluing I'm casually describing is in fact an equivalence relation. Or maybe it might not be good. I don't know. I'm not your mom. At least for now, let's start with a square. We're going to specify which sides to glue together and in what direction to glue them, as opposed to just collapsing everything down like we did with the disk. So what we'll do is we'll label the sides of our square, and if two sides have the same label, then we glue those sides together. We'll also draw arrows on each of the sides, and that'll tell us the direction to glue. Essentially, just line up the arrows and glue in that way. Let's have an example to see how this all plays out in action. If you can picture it, think of literally cutting this square out and gluing sides A to A so that the arrows line up. If you can't picture it, literally print and cut this square out and glue A to A so that the arrows line up. When you're done, you'll see that the space you get is a cylinder. Hopefully that wasn't too difficult. But let me make one note here before we try another. By gluing together the A sides, we can think of this as building a cylinder. But it's often easier to think of this as, if I go up the top of the square and cross over the A edge, then I'll come out on the bottom of the square from the A edge. That's exactly what happens when we glue sides. Now, let's start getting to the cool stuff. Here's 4 identified polygons. We're going to talk about each one of them. First of all, note that all 4 of them are different, even if only subtly so. Each of them glues sides or not differently than the others. Even though it might look like a slight change each time, we're going to show that all 4 of these give dramatically different spaces. Okay, let's start with A. Try and visualize. Do it now because we're going to quickly get into things you can't even begin to visualize. Gluing these sides one at a time. First A, then B. Well, if we glue A first, then we have the cylinder from before, with each end labeled B. If we glue those B's together, then we get the donut. Actually, let's stop and think about this for a moment. If you've ever played Asteroids, then you know that you can fly your ship up the top of the screen and pop out again from the bottom, and if you fly off to the left, then you come out on the right side. What this means is you're not playing in 3D space like you might think, but instead on the surface of a donut. We did it, we did the quintessential topology thing, we made reference to a 41-year-old video game. We're so hip and relatable. Now let's think about B. It's a lot like the cylinder, but there's this slight caveat involved. You don't glue up the sides exactly. You have to introduce a twist. This one might be a little hard to visualize, but if you cut out a square and try it yourself, then you'll see exactly what shape you're supposed to get. This is a Möbius band. Cut it out and do it yourself, because a Möbius band is a really crazy space that you can actually hold in your hand. That piece of paper will have only one side and only one edge. Trace your finger along the edge of it and see. It's a really neat space. Okay, what about C? It looks a lot like the donut, but it also has this twist with the A's, like with the Möbius band. You can certainly try to cut out a square and glue, but you'll soon find it rather hard. That's because this is a shape that lives in 4 dimensions. It's called a Klein bottle. But hold on. It's called a Klein bottle. To see it in 3-dimensional space, we have to make it pass through itself here. But this self-intersection is not an intrinsic part of the Klein bottle. It also doesn't have an inside or an outside, just like the Möbius band doesn't have a front or a back. And you can also make a Klein bottle by gluing 2 Möbius bands together. I'll leave that one for you to figure out. Try doing it on the level of the squares that we draw on paper. I don't recommend actually trying to glue 2 Möbius strips together in our real 3-dimensional world. We could also imagine cutting it in half. Imagine only, please. To see that it really is 2 Möbius bands glued together. Or go watch that number file video, man. Why do I gotta do everything around here? Finally, let's think about D. That one's pretty crazy. It's got 2 twists in it. Do the 2 twists somehow cancel each other out, or do they make it even more complicated? Of course, they make it even more complicated, as if your brain wasn't bent enough already. This space is called the real projective plane, which makes sense if I define it a little bit differently than the way I am here in D. Anyways, I'm not going to say very much about this space other than to show you its picture. If the Klein bottle was hard to picture, this one is downright impossible. And of course you can keep going, gluing in different ways or using different polygons. It's a neat theorem, the classification of surfaces, that you can get every 2-dimensional manifold by doing this. Of course, I need to tell you what a manifold is, and what dimension is, and probably the words compact and connected. But if we did that, then the proof itself is elementary enough that we could do it right now. We won't yet, but we could. Not now, but maybe sometime. Look, all I'm saying is that if we knew these definitions and you put a gun to my head, we could prove it, okay? What more do you want? Okay, so what was up with that quotient map business at the beginning? Here's the definition. A map Q from X to Y is a quotient map if it is surjective, its image doesn't miss any points in Y, and U is open in Y if and only if the preimage of U is open in X. I mean, obviously this is the right way to think about it. It kinda is. Notice that Q is by definition going to be continuous. And notice also that if X mod an equivalence relation plays the role of Y, then we have the definition we cooked up of a quotient space. U being open if its preimage is open. Or equivalently, Y having the final topology with respect to Q. That's exactly what we did with the quotient set and the equivalence class surjection P. So in some sense, this feels like a nice generalization of the very visual gluing equivalence class definitions that we explored before. Except, funnily enough, it doesn't give us anything new. We can actually show that any possible quotient map Q from X to Y is just an equivalence class surjection. So there are no other examples. Before we do that though, we're going to talk about a better defining feature of the quotient map. Once again, we're going to get categorical. Okay, so a quotient map has the following property. If Q from X to Y is a quotient map, Z is another topological space, and F from Y to Z is any function, then F is continuous if and only if F composed with Q is continuous. Go prove that. It's basically what it means to put the final topology on Y with respect to Q. But now that we know this, we can show if Q from X to Y is a quotient map, and Y is a topological space that's given the final topology with respect to Q, then Y is homeomorphic to X mod an equivalence relation, for some equivalence relation, and Q is an equivalence class surjection. Here's the trick. We cook up the equivalence relation. Define an equivalence relation on X to be X is related to X prime if and only if Q of X equals Q of X prime. That is reflexive because Q of X equals Q of X. Symmetric because if Q of X1 equals Q of X2, then Q of X2 equals Q of X1. And transitive because if Q of X1 equals Q of X2 and Q of X2 equals Q of X3, then Q of X1 equals Q of X3. Then construct X mod that equivalence relation. There's a function P from X to its quotient, which just sends a point to its equivalence class, which is for a point X, the set of all X primes in X, where X prime is equivalent to X. But since we have the equivalence relation in hand, this is just the set of X primes in X, where Q of X prime equals Q of X. Now, consider this diagram. Wait, is the class of Q inverse from Y to the quotient set even a function? Is it continuous? Well, we really should first check that it's a function. So take a point little y in Y and send it to brackets Q inverse of Y, which is just the equivalence class of the preimage of Y, which is the set of X's in X such that Q of X equals Y, because again, we have the equivalence relation in hand. But that is the definition of an equivalence class in the quotient set. So it lands in the right space. So brackets Q inverse is a function. Is it continuous? Well, let's use that universal property I mentioned. Brackets Q inverse is continuous if and only if brackets Q inverse composed with Q is. What map is that composition? Well, let's compute it by plugging in Q of X for Y. But that's just the equivalence class of X, which that's P of X. So our diagram really is just this. And since we know P is continuous, that means bracket Q inverse is. But hang on, brackets Q inverse clearly has an inverse function which is also continuous. Brackets Q from the quotient set to Y. Okay, I mean we need to check that brackets Q is a well-defined function, but I claim that that's easy. The equivalence relation on X makes it so, by construction. So brackets Q inverse is a continuous function with a continuous inverse, and that means it's a homeomorphism. Y is homeomorphic to the quotient set X mod your equivalence relation. We can check that part off. And to see that Q and P are morally one and the same, all you have to do is see that they're both the function that you define the final topology on the quotient set with respect to. And thus concludes our proof. Here comes the little QED box. bunch of words to say that we basically just wasted our time and only ever need to think about quotients as literal gluing? Well, okay then.